as you guys probably already know, magnets have two poles. They have north and south. I don't know if you can see the N and the S, but on these magnets I have, the north is colored red and the south is colored blue. As you probably also know, this one's more faded, but it's still red and blue. You know, if you have like poles, they attract one another, and if you have unlike poles, they repel one another. You can chase around the desk. It's kind of fun. It's interesting. The interesting thing about magnets is that with electricity, you can have a positive charge, you can have a negative charge, they can be separate, and that's all good. With magnets, as far as we know, you can't have a north without a south. Here's another kind of magnet, horseshoe magnet, and one of the sides is south, well, that one's the north, I guess, and then this side is the south, it pushes away. And so that magnet has two poles. Now if I break this in half, and this was broken in half some time ago, now you'd think that one side would be north, that maybe this would be north and this would be south, but it turns out that the two pieces, that's the south, and this end of it is the north. You break a bar magnet in half that has north and south pole, and you have another a smaller bar magnet that has a north and south pole. So as far as we know, there are no just norths or just souths. Every magnet has two poles, and there's no theoretical reason why you shouldn't be able to have a monopole, meaning just one kind of pole. But well, there isn't one, as it turns out. And scientists have worked out, how magnetic monopoles would work, and there's no theoretical reason why they shouldn't exist, as far as we know, but they just don't. Magnets, much like charges, create electric fields. So I have here just a little container. It's just got these little bits of iron, little grains of iron. And iron is nice because it responds to a magnetic field. So I'm going to lay this magnet down, and then just so I don't have iron filings everywhere, I'm going to put this piece of paper over it and lay out some iron filings onto this piece of paper. And when I do that, you'll be able to kind of see the magnetic field produced by this magnet. I just take my iron filings and start sprinkling them around. You can start to see that they align in a certain direction. And that direction shows you what the magnetic field of this bar magnet looks like. Now, it's not a super precise way of measuring the magnetic field, but it does give you a general idea of what it looks like. And I'm sprinkling it on this way because if you spread it on too thick, then you just get a pile of iron and you can't see what direction it's orienting itself. If you spread it on too thin, and you can't see anything. There's not enough of it there. But you can sort of see the general curvature of the field. You can see it points out, it kind of curves around here. And this magnet isn't super strong, so you can't really see what's going on here. The field is strongest right next to the poles, and then just like an electric dipole, it runs from north to south, and it kind of does that loop sort of thing that we saw when we had a positive charge and a negative charge next to each other. But this magnet isn't strong enough that you can see how, it's not really aligning the iron very much in these regions up here. Okay, so that's what the field of a single magnet looks like. You can diagram the magnetic field a lot like we did our electric field. The North Pole is a lot like a positive charge in terms of the diagram, and the South Pole is a lot like a negative charge. And just like with our electric field, the field lines exit North Poles and they terminate at South Poles. And the magnetic field for a bar magnet does the same kind of looping thing that the magnetic field of a dipole did. When we had a plus charge and a minus charge, and it kind of looped around and touched them. The difference is that magnetic field lines are closed loops. There's a magnetic field inside the magnet as well. And so it makes this full circle all the way around, going through the bar magnet. And that's kind of what the magnetic field looks like. And you can see the direction it's pointing at a given point. Using a compass is a handy tool for doing that. Actually, before I talk about that, let me say something about the Earth's magnetic field. If we've got the Earth, you know, this is the North Pole, the South Pole. The confusing thing that kind of blows your mind is that geographic north, so the north, you know that the North Pole of the compass magnet actually points north, okay? And the reason that the North Pole of the compass magnet points north is because the Earth has a magnetic field, which is, we're not entirely certain why how the Earth generates its magnetic field, but it probably has to do with you know, the movement of the liquid metals in the core, but scientists are not entirely certain why that happens. Anyway, so the north end of the compass magnet points north, and you know, the north end of the compass magnet is attracted to south poles of magnets. You know, if I take my magnet and I bring it right here, the red part is the north pointing part, it points right toward the south. But when you just hold it up, the compass points north, which if it's too close to the magnet, so it's getting flipped around. But you know, north is somewhere off in this direction. And the reason that it points north is because geographic north on the Earth is actually magnetic south, and vice versa. So that's why the compass needles point north. They're actually pointing toward the magnetic south. And we can see what the magnetic field looks like if I take my magnet here and I look at where the compass is pointing. You can see right there, it points, you know, directly in. And as we move it around, we can see it kind of following that loop pattern, kind of following the pattern that I drew. You know, this is pointing out here, and then it curves around in that sort of loop shape that I drew. So you can see how that field curves.